Hey, this is Kenneth, and today we're looking at the Z80 breadboard computer again, and we're running a self-replicating program, or a computer virus, I guess. So what we've got here physically is on the breadboard, I've essentially just built a RC 2014 micro. And so I've just built this in breadboard form. And I've got the ROM selected to the small computer monitor so that over the serial port I could load this program in manually into RAM. And so I manually typed in the individual byte codes, which we'll go over, starting at address 8000, because that is where the RAM starts on this computer. So looking at the memory map for this computer, the ROM is 8 kilobytes starting from 000 to 1FFF, right? And so this right here, right now, is the small computer monitor, which is really just a little terminal prompt that lets you view and edit and dump and modify RAM locations. And so you can, from this ROM, manually load in a program in the SRAM and then tell it to jump to it and run that program. So that's what we've done here. The rest of the lower half of the address space from 2000 up to 7FFF is empty, so there's nothing there. And then we have a 32 kilobyte SRAM going from 8000 all the way up to FFFF. So I've loaded my little computer virus replicating program right at the beginning of this SRAM, which we'll go over. Looking at the program that I have written, so I wrote this down on paper, and then we figured out what the actual machine code is that maps from these operations to the raw binary, which is what we loaded in. So starting at 800, it's this 9-byte program plus a bunch of no operations. And really all it is it's a bunch of setup for the LDIR command. This is an operation that's really kind of neat. It's a block transfer command. So let's first talk about this so that you can understand what all the setup is. So looking at the LDIR command, it is a block transfer command that copies data from the address pointed to by the value of the HL 16-bit register, and it copies that data to the DE register. Right, and so when you call the LDIR command to tell it what block of memory to copy from where to where else, you're telling it copy a block of memory from HL to DE and do it, and the block of memory is as big as the value in BC. So we're using 3 16-bit registers here as the source address, the destination address, and the length argument to this opcode. And so I'm guessing that LDIR stands for load, increment, and repeat, because this command is kind of neat in that once it copies the 1 byte, right, because when you run this command, it can only copy 1 byte at a time, right, because the data bus here, the green LEDs, that is only 8 bits. And so it reads whatever memory contents is at HL, writes it to DE, it then increments HL, so it's pointing at the next source byte, it increments DE, so you're pointing at the next destination byte, and then it decrements BC, because we've copied a byte, and then it does a conditional jump back to byte, program counter decremented by 2, if BC isn't 0. And this is kind of neat, and so we're doing like 5 different operations in a single 2-byte operation opcode, right? But this kind of part is kind of neat because what it means is that if we haven't reached the end of the block yet, because BC hasn't reached 0, we conditional jump back 2 bytes in our program counter, which puts us back at the beginning of the LDIR. And so we then enter the LDIR again, like HL was like we started 1 byte later, right? And so literally what this opcode does is it copies 1 byte, it checks to see if it's done, and if it's not, it tells your program to go back to the beginning of LDIR again and run it again. And so it just keeps repeating itself, this one opcode, over and over and over again until finally BC reaches 0, at which point it's done with the copy, right? So that's the opcode that we're showing off here. So unfortunately, since we need to do some setup for this virus before we go, and so I loaded this little program at A0FF, which is just another random chunk of memory that I just picked out in the middle of nowhere, and it's load into the HL register the literal value 8000, right? And so converting load HL 800 into binary, that is, and these are all in hexadecimal, 21. 21 is command load into HL a 16-bit value. And then after the 21, it's followed by 2 bytes, that is the literal to go with the 21 load into HL, a literal. And it starts with the least significant byte, which is 00, and then it's the 80, which is the top half, right? And so if we were loading FFFF, these 2 bytes here would be FFFF. Well, it would be FFFF, right? The Z80 is little endian, so the lower half of your 16-bit values is the first byte, right? And so we're loading into HL 8800, and then we're jumping, so we're setting the program counter also to 8800. So jump to a absolute 16-bit address is C3, and then we're jumping to 8000. So why we're doing this is because this program assumes that HL is loaded at the beginning of the program with the beginning of the program, right? And so ideally, if there was some way to copy the program counter over to HL, we could have skipped this part and had the first operation here be load into HL from the program counter, but you can't read from the program counter like that. Or at least not that I could tell reading the Z80 manual. So here's the program. And so what this program does is it first, these 2 operations load into D from H, which is binary machine code 54, and load into E from L, which is 5D. These 2 commands copies the current contents of HL into DE. Now remember, HL is currently pointing to the beginning of the program, and so we're essentially also then just duplicating that, so DE also points to the beginning of the program. We're then loading into BC the absolute value, the constant 0010, which is 16 in decimal. And so loading a constant into BC is the machine code 01, and we're loading 0010, so the arguments that follow the 01 are 0010, right? Little endian, so it's the 10 is first, and then the 00. And so to run the command, what we want to do is, I'm saying that the whole block that I want to copy is 16 bytes, or in hexadecimal 10. And that's why we're loading that into BC. So ideally, we could just add BC to DE to get DE to point to not here, but the end of this block, of the end of this program, so that we could then start copying stuff over. Unfortunately, the DE register doesn't have as many features as the HL. So you can't add something to the DE 16-bit register, but you can add something to the HL register. And so after loading BC with the hexadecimal 10, that is the length of the program, I'm adding to HL BC. And so now, instead of pointing to the beginning of the program like we want, HL is now pointing to the end of the program, which is not what we want. We want to copy from the beginning to the end, not from the end back to the beginning. And so we then, after running add HL BC, which is 09, we exchange DE with HL, which is EB. And so this tells the Z80, take whatever's in the contents of HL, move it to DE, whatever's in the contents of DE, move into HL. So it just swaps those two registers, exchange. Then we call the LDIR command, and that's the E0 or EDB0. And this is the command that sits there and does all of the work that we've set up here, my copying 1 byte, jumping back to itself conditionally, and just boom, 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 and then no ops. All right, and so that's the whole program. So looking at this front panel display that I've built, we can see that we're currently at the yellow is the address bus, so we're currently at A0F9, and so we're a few bytes before this little stub that loads, sets up HL like we need it, and then jumps into our program. And so we're at the beginning of this machine cycle, so we can see that our M1 light is lit, and we're reading from memory, and we're fetching a no op. So there's a no op right before our program. So we do a machine clock cycle, and then another clock cycle, and normally on the third clock cycle of a no op, the refresh signal would be active, the memory signal would be active, and on the lowest 7 bits of the address bus, the R register would be loaded so that if we had dynamic RAM, they would know which column, or group of cells to refresh based on, the lowest 7 bits, which is the R register, which just counts from 0 to 227. I found that really, I thought that showing the R register, which would be a totally random arbitrary number that doesn't have anything to do with what we're talking about, would be confusing. And so based on the refresh cycle, I've blanked out the address bus. And so the R register is actually being loaded on the data bus, but I've turned off the LED. So that's why we can't see that right here. All right, and we're now one machine cycle late. We're now one address later. So we're at A0FA, right? And so we're gonna just step through a few no operations here, right? And you can see the program counter is incrementing 1 byte on each no operation. And so now we're at A0FD, and we're, again, M1 fetching an opcode, reading from memory, and it's a 0 because it's a no op. There's A0FE, also a no op. And here we go. All right, so we're now at A0FF, and we are fetching 2-1 as an opcode, all right? And so 2-1 is the machine code for load HL with a 16-bit constant. And so this is telling it we're loading something into HL, and the next 2 bytes are going to be what you're loading into HL. And so again, we have the DRAM refresh. So again, whenever this light's lit, like it's doing a refresh, don't worry about it. And so now we're going to see it not do a opcode fetch, so a new M1 cycle. We're instead going to see it just do a read from memory at the next address. So the next address after A0FF would be A100. And so this is the low half of what we're loading into HL, which is 0. And now we're going to A101, and we're loading the top half of what we're putting in HL, which is 80, right? And so we're now loading the pointer 8000 into HL so that it is at the same value as the beginning of our program. And so it thinks about it, and we're on to the next machine cycle, right? So we can now see we're at A102, M1, new machine cycle, read from memory, and we're reading the C3, which is the opcode for jump to an absolute 16-bit pointer. And so this is us jumping to the beginning of our program. DRAM refresh, fetching the low half of our 16-bit pointer for the jump, fetching the top half, right? So we fetched 0, 0, 8, 0, and so we're going to now jump to 8, 0, 0, 0. And it thinks about it, and we can now see we're at 8, 0, 0, 0, right? And this is because of the jump, and we're now fetching the first instruction of this program, right? So now we're starting the program. This is where it starts. All right, so we're doing an opcode fetch, read from memory, and we're reading 5, 4, right? And so this is the load. So 5, 4 is the load from register H, from H, copy its contents into D. And we're now doing the same thing, except we're at 5D, and so we're copying from L to E, right? And so those two commands have copied HL. Looking at our program here, these two commands have copied HL into DE. And so now both HL and DE point to the beginning of our program. All right, next instruction. So we're now at 8002. We're, again, M1 reading from memory, and we're reading the value 0, 1, which is the machine code for load a constant into BC. All right, and so the next 2 bytes after this will be the constant that we are loading into BC. Little endian first means that the first byte that we're going to be reading is the 1, 0 in hexadecimal, so this is the length of our program, 16 bytes. And then we're reading the top half, which is 0, 0. And we're now on to the next operation. So after the load BC with the constant, we're now adding BC to HL. So HL is getting BC added to it, which is the operation 0, 9. Right, and this one's going to take a little bit of work because we're actually now doing like 16-bit math. And so this is like the processor just kind of putting something out on the address bus for who knows why, because there's none of these read or write or I/O or memory signals are active. So this is being ignored by everything. And it's going to take several clock cycles here for the Z80 to perform that calculation. So at this point, HL is pointing to the beginning of the program plus BC, so it's pointing to 8010, and DE is pointing to 8000, which is the opposite of what we want. And so the next operation, M1, read from memory, is EB, which is exchange DE and HL. And so this is what flips DE and HL so that we have the right value in the right registers for the LDIR command. And that's it. It's a pretty fast command. And so now, this is the beginning of the LDIR. So this is where the magic happens. 8007, new fetching an opcode, reading from memory, and we're reading the value ED, right? And this is the first half of the LDIR command. ED is a whole set of other opcodes that are actually 2 bytes long. And so it's a whole, I think there's like 5 chunks of opcodes that are these 2 byte opcodes instead of the standard 1 byte opcode. And so a little bit unusual is that 4 clock cycles later, we're now at 8008, and we're still on the M1. Since the first byte of the opcode was ED, we told the processor, this is a 2 byte opcode for this like whole set of block operations. And so we're still on the M1 cycle, and we're fetching the B0, which tells it what block operation we're doing, which is the LDIR. And this is where it gets wild. Now, since we've set up, let's see, going back to here. Since we've set up HL to point to the beginning of our program, DE to point to the end of our program, and BC to be the value of the length of the block we want to copy, this will now read from HL, write to DE, do a whole bunch of math, and then do a conditional jump back to 8007. So now we can see we are at address 8000, which is the contents of HL. We're doing a read from memory, and this is the value that happens to be sitting in RAM at HL. And now we're at pointing to address 8010, which is, this is the contents of DE, and we're in memory performing a write. So we're now writing to memory 54, which is the value that we just read from 8000. All right, and so that's the reason that I picked 16 bytes as my program length, is so that it's real easy to follow where we are in the program versus which block of RAM we're operating on. And so now the contents 54 is in both 8000 and 8010, and the Z80 now has to perform all of the bookkeeping, which is increment, increment, decrement, conditional jump. And so it is now not doing anything and thinking for a while about what the heck is going on. And now we can see we have jumped back to 8007, and we're starting the whole thing over again, right? M1 read IO. This is the ED that is the, block transfer command opcodes. And now we're reading the B0 from 8008, right? And so this is the exact same thing that we've already seen, but now the big difference is actually only internal to the Z80, and we can't see it, which is that HL now points at 8001, and DE now points at 8011. And so we're now going to perform the same copy, just 1 byte later, right? And so we can see here's the 8001, which is the 5D of the load EL. And we're writing it then to 1, 1. And so this is going to run 16 times, right? So there's the opcode fetch, read address 8002, and write it to 8012. Think about it, and relative jump back to 8007. Play it again. Right? So now read the value at 8003, write it to 8013, right? And so you can see as we work our way through here, this is going to copy the whole contents of this entire program, which is these 9 bytes of our actual operations plus a few no-ops at the end, just for, fun, because that's what I like to call as fun. It's going to copy it over, right? And so every time that we go through this copy, BC is getting decremented. So the BC register started at 16, and every time that we do one of these copies, right? And so here's the read, and then there's the write. It's now decrementing BC, so we're getting closer to 0, at which point we won't do the conditional jump back to, won't do the conditional relative jump back to rerun the LDR command, because at that point when BC reaches 0, the LDIR command is done. And so I need to not zone out here too much, right? So that's address A. And so now you can see we're actually getting into the no-ops. So these are the no-ops at the end. So we're currently reading, let's see, this is at address B. So that's 9, 10, A. So I think we're currently reading that no-op in our program and writing it to the future location that we're running. I hope this is the compelling YouTube content that you guys come here for. All right, so there's so we're reading E and writing it to 1E. All right, and so now we're at 8007, so we're reading the LDIR command again. And this time it's going to be so much more exciting because BC has now reached 0. And I just know that because I've been counting along with it. And so we're reading from 800F, which is the last no op in our program. We're now writing to 801F. And now, this is where it gets wild. We didn't jump back to 8007. We're now at 8009. Right, and so we finished, and we're now doing an opcode fetch, reading from memory, and it's a no op. We're now at address 800A. We're doing a no op. 800B, doing a no op. 800C, doing a no op. 800D, no op. 800E, and a no op. 800F, and a no op. 8010, and the new opcode that we're fetching is 54, which is load D with the contents of H. And so this is the beginning of our program again, but we're no longer at 8000, we're at 8010. And so the whole program is now copied over. Now, the cool thing is, since LDIR increments HL, HL now also happens to point to 8010, and so we don't need to edit HL, we just need to calculate the new destination address and run it. And so we could step through it again, which I don't think you want to do, but if I instead move the clock over to my 75 Hertz clock source, this is the program running, and it's self-replicating itself. So we now see that it's copying itself from 8003 to 8004, and you can kind of start to see the pattern of when it's in the LDIR loop, there's the read and the write, and then when it's going through everything else, it's bam, 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 bam. Now we're in the loop again. Now we're doing the no op slide. Now we're doing the loop again. And so this computer will now sit here and just keep copying this little program that we wrote into the next 16 bytes of memory until we run out of memory, which will be at, right? So we started here and we're doing this self-replication thing, and that's going to happen all the way until it gets to the end. And at that point, it's going to try and copy itself into the first 16 bytes of the ROM, which ROM stands for read-only memory, and so it's not going to care. And then at that point, it'll die. But I figured that this would be an educational way to see this computer step through raw machine code and understand the LDIR command, which I think is really, I believe that's one of the big additions that the Z80 architecture added, and so that you could, not necessarily quickly, because it's like the LDIR command is like 20 clock cycles, but in only 2 bytes of program space, I was able to fully describe, I want to copy this whole block of memory from here to here. And so it's a very space efficient way to do a block copy like this. And I thought that would be interesting to step through it. So I hope that you learned something here. So thanks for watching. I'm continuing to have fun with this breadboard computer. If you don't feel like actually building all of this, you can just go on Tindy and get the RC 2014 micro. As I really have no different, like the display here is custom, but everything on the breadboard really is just this, with the exception that I brought the refresh line out to one of the user pins so that the refresh line could blank the address bus on refreshes so that you don't see that. But everything here, like this ROM is actually the first half of the ROM that comes with the micro, and so we're currently at ROM bank 2, and so that's why we're running the small computer monitor that comes with the RC 2014. And so I've been having a lot of fun. Thanks for watching. More updates will absolutely come to follow.